Okay, so we can now begin discussing the idea of continuity. This was an idea that had existed for a while. You can geometrically you can talk about it in terms of a curve without any breaks or anything like that. But to do analysis, to do calculus, it's nice to have a more arithmetic definition, a more analytical definition. And so Euler had ideas something like a continuous function is one that can be expressed by a single expression. That is not a piecewise defined function. But there are clearly issues with that. I mean, just think about using that expression to try to do the things that we need to do with continuous functions nowadays. It's just hard to work with. Okay. The other issue is that it's very ambiguous. What do you mean by a single expression? Okay, so maybe a piecewise defined function that's not continuous. But what about piecewise defined functions that are continuous? Like, this, I can, define a function that's, like this, and then like this or something, right? That would be a continuous function, okay? It'd be a piecewise defined function. It's continuous by our notion, by our modern day, how we understand continuous functions is continuous geometrically because there's not a break in it, that sort of thing. But then what about functions like the square root of x squared, also known as the absolute value function? That's given by one, that is either given by one expression, like I just said, or you can give it as, minus x when x is less than 0, and then x when x is greater than or equal to 0. So there's it's not only is the definition not easy to work with, it's also ambiguous in terms of knowing which functions are continuous and which functions are discontinuous. It seems really that Euler just had in his mind what a continuous function is, and he sort of described it for the rest of us. He sort of condescended to the rest of us to give us an expression like a continuous function is one expressed by a continuous function is one expressed by a single expression, which is fine. We often have to do that before you're really pressed to give a definition. Cauchy sees a problem with this in a number of ways. But again, he just really didn't like this lack of rigor in analysis and calculus. So he has this definition of limit, and so with this definition of limit, he gives a definition of continuity. But what's important to remember is that he was still not defining continuity as a local property. So the way he defined continuity would essentially be our definition of what it means for a function to be continuous on the whole interval. He says if you look at a function between 2 points, and if for every x in there, the limit as a approaches x of f of a is equal to f of x, then we say if that's true for all values of x in the interval, then we say f is continuous. Okay, so for him, the property of continuity was like the property that went with a function and its domain. Okay, a function is continuous on its domain. Okay, now for us, remember, continuity is a local property. We talk about a function being continuous at a point. And then, if it's continuous at all of the points in an interval, then we say the function is continuous on that interval. But really, the fundamental definition we use for continuity is continuous at a point. Now, it actually turns out that 4 years earlier, the Czech mathematician Bolzano actually had come up with a very similar definition to this, and he was trying to prove the intermediate value theorem. Okay, so the intermediate value theorem says that if you f of a is equal to 0. Let me get it. I don't know which is mirrored here. If f of a is equal to 0 and f of b is if f of z is less, if f of a is less than 0, f of b is greater than 0. There has to be some point at which f of x is equal to 0. So we'll talk about that a little bit later. That's one of the reasons that Bolzano was trying to do this. He wanted to give a proof similar to Cauchy. He wanted to give a rigorous and precise proof of the intermediate value theorem. But to be able to do that, you need to have, there's a few ingredients that you need, but for sure one of them is going to be something like what the precise definition of a continuous function is. Okay. So along these lines, so there's several sort of threads happening at once. One of the threads is what I just mentioned, and one of the threads is going to be sums of series. So Cauchy was the first one to give the definition of a sum of series in terms, the sum of a series in terms of the limit of its partial sums. Because remember, he sort of had this idea of limits, And now he's applying it to a sequence in kind of a natural way to get this idea of the sum of a series. So to remind you, if we have a series written in modern notation, something like this, k equals 0 to ak, this is defined as the limit as n goes to infinity of the sum k equals 0 to n ak. Now, for every finite n, this sum is perfectly well defined. It's a sum of a finite number of numbers, so there's no ambiguity at all for each value of n, and then we take the limit of that as n goes to infinity. Okay, now what Cauchy realizes is that for a sum to converge, the limit of each term has to go to 0. He realizes for a sum to converge, the limit of each term has to go to 0. But remember, this is not sufficient. It's necessary, but it's not sufficient. So for example, if you look at the sum, k equals 1 to infinity, 1 over k, this famously does not converge, yet its terms go to 0. So it is a necessary condition for the terms to go to 0, but it's not sufficient. That's why we call this the test for divergence when we teach this in Calc 2. But he does come up with another criterion. This is called the Cauchy criterion. And essentially what it says is that if the tails of the sum go to 0, that is, if we have something like this, the sum k equals m to n, if this goes to 0 as m and n go to infinity, if the sum satisfies that, okay, then if the sum satisfies this quality here, the series satisfies this criterion here, then it is convergent. And furthermore, this is necessary and sufficient. So series converges if and only if it satisfies the Cauchy criterion. Now, if you know about Cauchy sequences, if you know what a Cauchy sequence is, notice that this is a very Cauchy sequence statement. So these ideas are all kind of bound up together. Okay, these are the motivations for studying various of these things. Okay, now there are two other mathematicians. Bolzano, already mentioned him, and da Cunha, who was a Portuguese mathematician. Bolzano was a Czech mathematician. Da Cunha was a Portuguese mathematician that had already solved. They had already gotten here before. Cauchy, Cauchy, though, is working from the center of Europe, and these two were working from the outskirts of Europe. And before internet and things like that, it was hard for information to travel. Now, I don't want to say things that I don't know about, but also these same people were, not these same people, but these same groups of people were sort of getting all bent out of shape in a nationalistic way over different notions and ways to write, derivatives and stuff like that. So there might have been some sort of, only looking at the people closest to you on purpose, but also even if they weren't trying to do that, these people were on the outskirts of Europe. So, how is it just impractical to get the information? Anyways, I just want to point out that these guys got there first. Maybe there's other people that got there even before, and this is something that you could read more about in the book. There's biographies of both of these people. Bolzano is somebody that we're going to come back to later. I misspelled his name here. It's that A should be an O. That first A should be an O. Okay. All right. So we are wanting to start to develop some things. Now, I mentioned that Cauchy made a mistake in terms of, I mentioned in the last video that Cauchy made a mistake using his definition of continuity. I'll get to that, but one of the things that we're going to talk about first, and again, I misspelled Bolzano's name here, again, is the least upper bound property. So what he proves, and he proves this using series, this is very interesting, is that all bounded sets have a least upper bound. All bounded sets have a least upper bound. Now he states this a little bit differently. What he says is that if you have a set of numbers, a set of real numbers, and you know that all the numbers below below some certain number are in that set, and then maybe there's another number, all the numbers below that certain number in the set, and so on and so forth. There's a greatest one of these such that all of the numbers less than that number are in the set. Okay, so let me write this what he says. And I'm gonna and again, he doesn't use the language of sets, so I'm gonna translate his language a little bit into our way, the way that we would talk about things, just because I think the main idea is still there. So assume S is a set such that for all x less than some number little u, x is in S. Okay, so assume that S is a set such that for all numbers less than u, x is in S. So for example, if we think about all of the numbers less than 325, okay, this set has that property. I could take 325, but I could also take 273 because 273 is less than 325. Okay, so that's what this is saying. Okay, there is a capital U such that all x less than u are in S, and if u prime is bigger than u, u prime does not have this property. Okay, now again, we're going to talk more about the construction of real numbers later, but he uses this, again, to prove the intermediate value theorem. And I'm not going to give his proof of the intermediate value theorem, but this is what he does. This is what he uses to prove the intermediate value theorem. And in his application, let's say we have a function where a is less than b, and f of a is less than 0, and f of b is greater than 0. He's going to say, I'm going to look at the property. I can assume that that f of x is less than 0 for all x less than a. In fact, I can just assume that f of x is equal to f of a for x less than a. And then the property of numbers, the set of numbers that he's going to think about, are going to be all of the x's where f of x is less than 0. So let's look at all the x's where f of x is less than 0. And clearly it's going to fall into this type of category here. We're going to look at all of the numbers where f of x is less than 0, and then big U here is going to end up being where f of x is equal to 0. So I want you guys to read about this proof on your own and ask about it in the comments, but they're in the discussion, but this is one of the things that we're talking about. Okay, this is his application of this. And like I said, when we talk about the construction of real numbers later, we might come back to this depending on, I don't know, my mood. Okay, so now in this same stream of ideas is this idea of uniform convergence. And Cauchy proves needs to be an air quote here because he made a mistake, but he proves the following theorem. I'm going to write what he proves, okay? And again, the proof is wrong. The statement of the theorem is wrong, and his proof is wrong, but I'm going to write it. It says the following, and again, I'm going to kind of translate it into more modern language, but the ideas are the same. So if fk is a sequence of functions of continuous functions, if fk is a sequence of continuous functions, and fk of x converges to f of x, then f is continuous CTS at x. So maybe this should say something. If fk is a sequence of functions that's continuous at x, like that to be a little more precise. And fk of x converges. There should be an error there. Converges to f of x, then f is continuous at x. So if we want to sort of say this in a quick way, we would say the limit of a sequence of continuous functions is continuous. Now, this is not true. Okay, this statement, the thing here as stated, is not true. I've given one example here. F of x equals x to the power of k when x goes from 0 to 1. And then f of x is equal to 1 when x is bigger than 1. So what's happening with that function? Well, so let's say this is 1. The graph of this function, when k is equal to 1, is going to look like this. That's what the graph of the function is going to look like when k is equal to 1. That's what the graph of the function is going to look like when k is greater than 1. Because remember, f of x is equal to x to the power of k when x is between 0 and 1, and it's just equal to 1 over here. Okay. Now, as k increases, notice what happens. Like when k is equal to 2, it's going to be a parabola like that. When k is equal to 3, it's going to be that. When k is equal to 4, it's going to be that. And we can see what's happening here is that if x is between 0 and 1, it's a number that's less than 1. It's between 0 and 1 being raised to higher and higher powers. Well, that's going to converge to 0. So in the limit function is going to be 0 from x equals 0 to 1, and it's going to be 1 like this. Okay? And so we can see what's happening. Values of x that are closer to 0 are going to be converging much faster than values that are close to 1. Because 1 to the power of k is always equal to 1. Okay, so 0.9, if you do 0.9 to the power of k, 0.9 times 0.9 times 0.9, that's pretty close to 1, but it's still going to go to 0 pretty quickly. 0.9 to the power of 4 is still pretty small. I mean, it's not like 0, but it's just barely 1/2. Or it's maybe just a little bit more than 1/2. So 0.9 to the power of 10 is going to be, very small. Okay, but you also have numbers that are like 0.9999999999999999999999999999999999999999999999999999999999999999999999999999999 a million nines or whatever. And now when you raise that to the power of k, it's going to take a lot longer for that, to be less, to go down to 0 than it is, 1/2 or 0.99 or something like that. So we do not have an even rate of convergence here. So that's going to be the issue. But I want to discuss Cauchy's proof here. Because the key, one of the things he does there's nothing wrong with, but I'll show you what is wrong with it. Okay, so what he does is he says, okay, well, I want to look at f of x plus a minus f of x. And what he says is he says, okay, I kind of want to make it so that as a goes to 0, this goes to 0. F of x plus a minus f of x goes to 0. That's just a statement that I can make x plus a arbitrarily close to f of x by making a arbitrarily close to 0. That's just what this is saying. And he uses the triangle inequality to say, okay, this, well, let me even back up a step. He says, okay, this is equal to f of x plus a. See, he doesn't know that f is continuous, but he knows that all of the fk's are continuous. So this is equal to f of x plus a minus fk of x plus a. So I added that, so I subtracted that, so I need to add it back in. Fk of x plus a minus fk of x. Okay, so those two cancel to equal to 0. I have an fk plus x, so now I'm going to do fk, I'm adding in an fk of x, and then finally subtracting f of x. Okay, so these are just equal because I've added and subtracted the same term here and here. Okay, now what he says is, well, by the triangle inequality, this is less than or equal to all of these. Okay, now what he says is the following. He says, okay, f of x plus a minus fk of x plus a. Well, the fk's converge. The fk's converge to f. So I can make this less than whatever small, by taking k sufficiently large, I can make this less than whatever I want it to be. So I can make this less than epsilon over 3. fk of x plus a minus fk of x. Okay, so here he says I can take, in this first term, to get this epsilon over 3, he says by making k large enough, I can make this less than epsilon over 3. For this, notice it's the same k. And what he says is I can make this difference as small as I want by taking a sufficiently close to k. So this is going to be less than epsilon over 3 if a is sufficiently close to x. And then down here, something similar. Fk of x converges to f of x. So by taking k sufficiently large, like I'm going to have to figure out the value of k from here, the value of k from here, and I'll take the largest of those, and this is going to be epsilon over 3, and this is equal to epsilon. So in other words, by taking k large enough, and by taking x close to a, I can make this less than epsilon. Okay, so what's wrong with this? So pause the video for a moment to see what the issue is, to see if you can spot what the issue is. So let's think about what needs to be proven. What we need to say is that for a given epsilon, I can make a small enough, the absolute value of a less than delta. For all epsilon greater than 0, there's a delta greater than 0, such that if a is less than delta, this inequality is true. Okay, so what's the issue? Here's the issue. The issue is that if I need these two terms here to be less than epsilon over 3, and I need this term to be less than epsilon over 3. Okay, so how can I do this? Well, I'm going to pick a k. I'm going to pick a k such that this is less than delta. Such that if k is, I'm going to pick an m such that if k is bigger than m, this is going to be less than epsilon over 3, and this is going to be less than epsilon over 3. Okay, but can I do that? Is there going to be one k that works? Because this it can't just be for one value of a. This has to work for all values of a, such that the absolute value of a is less than delta. Okay, so I need to find an m such that if k is bigger than m, this and this are going to be less than epsilon over 3 for all a that are less than delta. That's what needs to happen. Because this inequality needs to be true for all a whose absolute value is less than delta. So it means that both of these inequalities, for this idea to work, both of these have to be true for all for all a whose absolute value is less than delta. But can I get that to happen? And if you think back to the example that I gave before of x to the power of k, take x equals 1, and you'll see that you cannot do this. There's not going to be there's not going to be one single value of m such that if k is bigger than m, f of x plus a minus f of 1 plus a minus fk of 1 plus a is going to be less than epsilon over 3 for all values of a less than some number. Because we can always take, I can always make a sufficiently small so that 1 plus a is sufficiently close to 1, 0.9999999999999, and then that to the power of k is going to be greater than epsilon over 3. And then you can say, okay, well, what about if we make delta smaller? Okay, that's fine. I can just pick a value of a that's even smaller, and so x plus a is going to be even closer to 1, maybe 0.1 trillion nines, and you raise that to the power of whatever k we're having to work with, and that's also still going to be greater than epsilon over 3. Okay, so the idea is that this inequality, f of x plus a minus fk of x plus a, and this inequality right here, this has to be less than epsilon over 3. That has to be less than epsilon over 3 for all a less than delta. And essentially what can happen is you can make a get closer and closer to 0. If a gets closer and closer to 0, if your delta gets closer and closer to 0, it could turn out that you need to take k larger and larger and larger. And it could be that you always, the closer you make delta go to 0, that just gets bigger and bigger and bigger. The k just gets bigger and bigger and bigger. And there's not going to be one value of m such that for all k greater than m, this inequality and that inequality are going to be less than epsilon over 3. Okay, so then the idea of uniform continuity comes in. Okay, and this is one of the major things that Weierstrass is able to do. So he begins by making a clean distinction between the convergence of a sequence of functions and a sequence of numbers. He makes a difference between, he makes a distinction between the convergence of a sequence of numbers and the convergence of a sequence of numbers. Now, this is one of the issues that Cauchy was having, because Cauchy was saying things like arbitrarily small increments here, arbitrarily small increments there, without really considering how these arbitrarily small increments were relating to one another. And this is exactly what Weierstrass does, or this is what he doesn't do, I should say. And what he does is, I didn't want to get rid of that. Let me, f of x plus a minus f of x. Okay, so what he does is he gives, I'm not going to rewrite this, but what he gives is he gives a notion of uniform continuity. So that's the second bullet point here. I'm just going to read it. It says the sequence of functions converges uniformly on a set if for all epsilon greater than 0, there is an in such that for k greater than n, fk of x minus f of x is less than epsilon for all x in the set. What convergence tells us, if we just think about a function converging pointwise to a limit, all that tells us is that for a fixed x, or a fixed x plus a here, by taking k sufficiently large, I can make this close enough to 0. But that how sufficiently large I have to take k is going to depend on the argument. What we need is a notion of convergence that doesn't have that dependence. That's exactly what Weierstrass came up with, and that is uniform convergence. That is one of the most important properties. So now what this is saying is that it says for all values that we can plug into our function here, if k is bigger than n, let me say it the other way, for all epsilon greater than 0, and for all functions that we can plug in here, there is an in such that if k is greater than n, this difference is going to be less than epsilon. And this is true for any values that we can plug in there. In other words, the k does not depend on x plus a. Whereas before, it potentially could depend on the x plus a. And if it doesn't, we have the situation of uniform convergence. Okay, so now everything works well, because here's what we can do. Let epsilon be greater than 0. We can pick a k such that f of x plus a, we can pick an n such that if n is greater than k, f of x plus a minus fk of x plus a is going to be less than epsilon over 3. And we could use the same k for x. So the idea is that for all values that we're considering in our domain, we can make this less than epsilon over 3, and I can make this less than epsilon, this bottom one less than epsilon over 3, simply by taking k big enough. Okay, so I've taken k big enough so that this is less than epsilon over 3, and this is less than epsilon over 3. Now the next thing that I do is I say, okay, for that particular value of k, for that particular function, fk of x, I'm going to choose a delta such that if the absolute value of a is less than delta, then this quantity is going to be less than epsilon over 3. And now the proof follows. Okay, but the key idea here is uniform convergence. And if we didn't have the idea of uniform convergence, we could not make this. So the most general statement that you can make in terms of the regularity of the limit of a sequence of functions has to involve some notion of uniform continuity or something like that. Just a regular point-wise definition of convergence of a sequence of functions is not going to work. Now, once we have this idea of convergence, we have two different types of convergence now. We have a point-wise convergence, which simply says that fk of x converges to f of x for all values of x, but the convergence could be at drastically different speeds. What this is saying, this notion of uniform convergence, is that everything is kind of being pressed down to the limit uniformly. And this idea of uniform convergence is where we get a lot, if we have uniform convergence, then a lot of other things are true as well. So it is a topological property. Now, last thing that I'll mention about this before I end this video is the notion of pointwise convergence is probably the most elementary and the most naive one to deal with. However, topologically speaking, it is not a good notion of convergence. Okay, now if you don't know much topology, or measure theory and this sort of thing, I don't know how much you're going to get out of this, but you can, either stop watching, of course, at any point, or watch and try to figure out what I'm saying. So my claim is that point-wise convergence is not topological. What I want to say is that point-wise convergence is not topological. Now, what do I mean by that? Okay, what I mean is the following. If it is, then if we have a sequence of functions, fk, and this sequence converges to the zero function. This is not the number 0, this is the 0 function. Then for all neighborhoods of the 0 function, there is an n such that if k is greater than n, then fk is in that neighborhood. Okay, so if you have a sequence of functions that converges to the 0 function, the way that we would say this in a point set topological way would be that for all neighborhoods of the 0 function, there is an n such that if k is greater than n, then fk is in that neighborhood. Okay, on the other hand, this is sort of a definitional thing. So what this says is that if fk does not converge to 0, then there are infinitely many functions. What this says is that if fk does not converge to 0, then there is some neighborhood of 0 such that infinitely many elements of this sequence are not in that neighborhood. In other words, it says that if fk is a sequence of functions that does not converge to the 0 function, then there's a neighborhood such that there is a subsequence that's completely outside of that neighborhood. Okay, so let me see if I can sort of encode this a little bit better. Or write this a little bit better. So if fk converges to 0, then for all neighborhoods u, there exists an n such that if k is greater than n, fk is in u. Now, I don't typically like using a whole lot of symbols like this, but I need to condense. Okay, on the other hand, if fk does not converge to 0, there exists a neighborhood of u such that there exists a subsequence f sub nk that is outside u. Like none of the elements of this subsequence. Okay, so here's what we're going to do. So if you have taken measure theory, you know that there are some sequences that converge in measure to 0. That's what the n here, measure. But it does not converge pointwise to 0. Okay, so importantly, the fact that it converges to measure in 0 isn't so important, but we know it does not converge to 0. We know the sequence does not converge to 0. So what this tells us is we can find a subsequence. We can find a subsequence that is we can find a neighborhood and a subsequence such that f in k is not in u for all k. Okay, now I'm going to sort of abuse notation here. This f in k is a subsequence of a sequence that converges in measure to 0, so it also converges in measure to 0. So I'm just going to call this our main sequence now, because we don't care about the one that we came from. Okay, So I know that this sequence fk, which is technically a subsequence of what we started with, I know two things about it. There's a neighborhood such that there's a neighborhood of the zero function such that none of these fk's are in that neighborhood. But I also know this converges in measure to the zero function. Okay, now I'm going to use the following fact from measure theory. If I have a sequence of functions that converges in measure to zero, there is a subsequence that converges pointwise to zero. But this is just a subsequence of that. So if this converges pointwise to zero, it means that for all neighborhoods, there's an infinite number of these terms of the sequence that are in that neighborhood. But is a subsequence of a subset of a set of functions such that there is a neighborhood where none of them are in that neighborhood. Okay, so if this does truly converge to zero, then whatever this neighborhood is here, there should be infinitely many of these terms in that neighborhood. But this assumption here that we went over before says none of them are in that neighborhood. Okay, so what this shows is that even though pointwise convergence is a nice thing to deal with, it's sort of a naive definition of what it might mean for a sequence of functions to converge, it's just not good enough. Uniform convergence does not have this problem. Okay, this is a topological notion of convergence, and then there's other ones as well. So as analysis sort of expands at the rest of the 19th century and into the 20th century, we get even more ideas of what it might mean for a sequence of functions to converge. But for those ideas, you'll have to take one of our graduate level analysis classes to get more than what we've talked about here.